So we've just solved this problem correctly. Now, let me clarify something really quickly. 5 meters per second, this is how fast you move along whatever surface you are situated on. So if you're situated on the walkway, then you move at 5 meters per second with respect to the walkway. If you're situated on the ground, then you move at 5 meters per second on the ground. That's how fast you're going relative to or with respect to the thing that you're on. Okay, so now you get a little closer to the end and you realize you're not running towards Justin Bieber. There's the Bieber with his hair. You are not running toward Justin Bieber. That's your ex-boyfriend. Uh-oh. So what do? You turn around and you sprint the other way. Here's the walkway. And you can only run at 5 meters per second. There you are. Your neck doesn't look so good. Maybe you should see a doctor. Okay. Of course, you're going the other way now at the same 5. That's how fast you run. And the walkway hasn't changed directions. It still carries the floor there. The conveyor belt is being carried to the right at 1 meter per second. So now, what's the velocity of you, the person, with respect to the ground, or in the ground's frame? You can probably guess. You make the 5 negative, because it's to the left, and you add the 1 meter per second, moving to the right. And this evaluates to -4 meters per second. And that's the correct answer. How fast are you going with respect to the ground? You're going at -4 meters per second, or 4 meters per second to the left. How fast are you going relative to the walkway? You're going at 5 meters per second. And in fact, if the walkway were stationary, if this wasn't moving, then you would be going at just 5 meters per second with respect to both the walkway and with respect to the ground. But that's not what we have here. So there is no math whatsoever, no equation rather. We have not appealed to an equation. We've just been using our intuition to find the answer. So let's try and put some theory behind this. 5 meters per second or -5 meters per second. That's your velocity with respect to whatever surface you're on. That's just how fast you run on any surface, be it the walkway, the ground. So this is the velocity, in this case, of the person. What are you on? With respect to the walkway. That's the velocity of you with respect to the thing you're on, the walkway. 1 meter per second, we said, is how fast, that's how fast the walkway goes, and we didn't specify what it was with respect to. We just said it goes at 1 meter per second. So we know it's the velocity of the walkway, and if we don't specify what frame we're in, we assume the ground's frame. So that's how fast the walkway is moving if you're just standing on the ground, like Justin Bieber, or the boyfriend, ex-boyfriend. That's how fast the walkway seems to be moving to this person on the stationary ground. 1 meter per second. So there's an equation here. Do you see the equation? In both cases, let me get rid of some of this other stuff so we can see the equation. Good, there we go. In both cases, we found the velocity of the person with respect to the ground by adding the velocity of the person with respect to the walkway with the velocity of the walkway with respect to the ground. And we see that's true. But here's the thing. We made one negative because it was going to the right, and the others we let be positive because they were negative because it was going to the left. And the others were positive because they were to the right. When is it that we use sign to indicate direction? Oh yeah, we would do that with vectors in one dimension. But the point here is that these are vectors. These are vectors, and we just solved problems where the vectors were along one dimension, left, right, that dimension. Now, the specific, this right here, we are going to call a relative velocity equation. Relative velocity equations, they change. It won't always be a person or a walkway or the ground. The variables change, the objects change, but there are some rules for writing a relative velocity equation, and here they are. If you look at the right side, the inner subscripts are matching, they're the same. That's one of the rules for writing a relative velocity equation. The inner subscripts are the things added, if the velocity is added, must match. Likewise, the outer subscripts, P and G in this case, person and ground, have to match those on the left, the subscripts on the left. Those are the two rules for writing these equations. If you follow those rules, you will write correct equations. And that's how we write a relative velocity equation. Now, these are vectors, right? So we don't always deal with one-dimensional vectors. We can do problems with 2D vectors, and that is a little bit more challenging. So let's see what that looks like. Okay, so here's our problem, which will give us a taste of 2D relative velocity equations and problems. A boat is traveling at 4 meters per second north. With respect to a river. That's important. The river runs east and west, and the current is 3 meters per second west with respect to the shore. Find the boat's velocity, that's the unknown, the boat's velocity, magnitude and direction, with respect to the shore. So WRT is with respect to. First thing we're going to do is draw a picture. We have the shore here. River is running east-west. The boat is going north. The boat is going north. And what is the boat's velocity with respect to the water? It's 4 meters per second north. It's going across the river, as we can see. But the water is moving at 3 meters per second west with respect to the shore. So we've drawn our picture, but now we need to put subscripts. We need to put subscripts beside these velocities so we know what we're dealing with. 4 meters per second is the velocity of the boat with respect to the water. 3 meters per second is the velocity of the water with respect to the shore. Okay? So you look at these two velocities, and what are we looking for? We're looking for the velocity of the boat with respect to the shore. The magnitude and the direction. We look at these velocities, we see, there's a W on the left and a W on the right. So if there's a W on the left and a W on the right, then that means when we write our relative velocity equation, we're going to be adding two velocities, and W will be on the inside. W will be the inside variable because we have a W on the left and on the right, which means it's going to be the inside variable. Okay then, what's the variable that goes here? It's not that. It's B, the boat with respect to the water. What's the variable that goes here? Well, it's not this one because I just used that variable, so it must be this one, W sub WS. Let's get this away. Okay, and we have followed the rule. This means on the left side, what should the velocity be? Well, BS are the subscripts. The velocity of the boat with respect to the shore. And hey, that's our unknown. So this is working out really, really well so far. The problem has been designed so that our equation is instantly usable to find the unknown. here's what you may be tempted to do. You might be tempted to say VBW is 4, then VWS is 3, but this is clearly wrong. No, we don't want to do that. The equation that you just wrote, the relative velocity equation here, is for vectors, and these are 2D vectors. And this is going to be a 2D vector, or they are in 2 dimensions, I should say. And if they're in 2 dimensions, then the equation doesn't say add 3 with 4. Instead, what the equation says is it shows us how to draw our right triangle. It says take this vector, where is it? Here, it's the up arrow. Let me move this away. The equation says take this up arrow, add to it this left arrow, VWS, and the resultant, the hypotenuse, is V sub BS. So let's do exactly that. Let's draw the right triangle. Whoops. Let me go back. And down. Let's draw that right triangle. Extend page. We want to draw this one first, the X leg, and it's going to the left, 3 meters per second. Then we draw the Y leg, this one, connect them tip to tail, 4 meters per second. The resultant is, you guessed it, V sub BS. According to our equation, the resultant is VBS. And because the 2 vectors that we just added, because one was going north and the other was going west, we have a right triangle. So we're going to find the value of VBS and theta. There's theta. We use a little geometry. VBS is the square root of 3 squared plus, oh, that's a 3, 4, 5 triangle. So 5 meters per second. Theta is the inverse tan of 4 over 3. And what's that? It's about 53 degrees. And of course we need to attach the directions like east of west, or that doesn't make sense. No. So what is it? Theta is pointing, well, our reference is west rather. So our reference line is west. So from west of west, which way have we gone? We've gone north of west. From the reference, we went north, right? North, not south. Okay. That is our answer for part A. And now let's say there's a second part, B. The second part says, part B is this. If the river is 80 meters across, how long does it take the boat to traverse the entire river? Traverse is a great word. It means kind of to cross over or to go from one side to the other, to travel across, traverse. So, okay, they just gave us 80 meters across. Now, 80 meters is this. But the boat is going this way, 80 meters. That is a northward displacement, because it's traveling 80 meters. That's a delta y, since north is on the y-axis. So we are going to use, to answer this question, we are going to use our good old friend, constant velocity is displacement over time. We know delta y is 80 meters. We're looking for how long, that's delta t, how long is time. But what velocity do we use? I mean, we have 3, we have 4, and then we have the 5, the resultant. You select the velocity, which is in the same direction as the given displacement. Here, we have a y-axis displacement, so we have to choose the y-axis velocity, which lies on the y-axis. So we use 4 meters per second. So we plug in the value V